Imagine swapping out the standard stopwatch you use to time a race.
Okay, I'm with you.
And suddenly, the runners take an hour and 16 minutes to finish instead of their usual, I don't know, 8 minutes.
Wow. Yeah, that is a huge difference.
Right. You didn't change the distance. You didn't change the runners. All you did was change the tool measuring them, and the entire system just ground to a complete halt.
That is a terrifying scenario, honestly, if you're a software engineer waiting on a deployment pipeline.
Yeah.
But it is actually a very real thing that happened during what should have been a seemingly straightforward code migration.
Welcome to today's deep dive.
Yeah.
Today we are looking at a really fascinating slide presentation from 2026 by a developer who goes by the name Luck036.
Yeah, the title is Google Benchmark versus NanoBench, Migrating C++ Benchmarking Framework in the AI Era.
Yeah, on the surface, I know a C++ framework migration sounds like an incredibly niche topic. Maybe just a bit of standard software maintenance.
Yeah, it sounds like basic housekeeping, just updating tools. But when you look at the mechanics of why this migration happened and, the disaster it almost caused, it becomes this crucial case study.
And that brings us to our mission for today. We want to show you why simplifying code isn't just a matter of making things readable for human engineers anymore.
Right, it's way beyond that now.
It has become a structural necessity for survival when you have AI assistants writing and managing your code base.
Absolutely.
So we are going to unpack how a simple, well-intentioned swap to a lighter framework caused that massive benchmark slowdown, and how fixing it actually reveals a major blind spot in how we expect AI to understand our code.
And to really grasp the stakes of that slowdown, we first have to understand the arena, so to speak.
Set the stage for us.
Well, we need to know what this code is actually doing under the hood, because the math involved, that's what sets the trap later on.
Okay, so the project Luck036 is working on, it's called LLGO CPP. And it's a C++ implementation of something called the ellipsoid method.
Right, which is a technique used for convex optimization.
Convex optimization. Okay, for anyone who hasn't taken advanced calculus recently, how would you define that?
Good question. Convex optimization is essentially a way to find the absolute best possible solution to a problem given a really strict set of constraints.
Okay.
You can kind of visualize it like trying to find the absolute lowest point in a giant multidimensional bowl.
Oh, I see.
Yeah, the algorithm is systematically narrowing down the search space until it hits the bottom.
Got it. And within this AlgoGo project, the developer is testing two very specific variants of this ellipsoid math. They call them L and L stable.
Right.
And to the outside world, these two variants, they have the exact same interface. Like you plug the same data in, you get the same answer out.
Exactly the same.
But internally, they use completely different numerical approaches to get there.
Yeah, so the standard L variant, it uses a rank 1 update. And the key takeaway for this method is its computational complexity. It operates in O of n squared time.
Okay, let's unpack O of n squared for a second, just because that's critical to the bug we're going to talk about later.
Sure.
That basically means the time it takes to solve the problem grows quadratically relative to the data, right?
Yes.
So if you double the amount of data, the time it takes to process doesn't just double.
It quadruples. That's the perfect way to look at it.
Right.
A tiny test might run in milliseconds, but a slightly larger test can suddenly bring a CPU to its knees.
Okay, so that's the standard L variant.
Right. Now, the second variant, L stable, also operates in O of n squared time, but it uses a different internal mechanism. It's called an LDLT factorization update.
Okay, LDLT factorization. How does that differ from the rank 1 update? Like, what's the actual benefit there?
Well, it comes down to how computers handle decimals.
Decimals.
Yeah. I mean, matrix math involves an enormous amount of multiplication and division. And when computers calculate floating point numbers, essentially numbers with decimals, they have to round things off at this microscopic level.
Because they can't hold infinite decimal places in memory.
Exactly. And over thousands of calculations, those tiny rounding errors, they accumulate. And your final answer can drift away from the true mathematical solution.
So it just gets slightly less accurate over time.
Right. So LDLT factorization breaks the matrix down differently. It separates it into lower triangular and diagonal components.
Okay.
By isolating the math this way, it keeps the numbers in a safer range and essentially prevents those rounding errors from snowballing.
So it provides much better numerical stability.
Exactly. Hence the name L stable.
So testing L versus L stable, it's kind of like having identical twins run a marathon.
Okay, I like this analogy.
Right. They look the same, they run the same route, and ideally they cross the finish line at the exact same time. But one twin L stable is wearing highly specialized shock-absorbing running shoes.
Yeah.
And we need to know if those shoes actually make the run smoother and more efficient.
Yeah.
But to do that, we need incredibly precise stopwatches to measure every single footstep without accidentally tripping up the runners in the process.
That's a great way to put it. The stopwatch analogy works for the basic idea, but, it's actually a bit too simple for what a benchmarking framework actually does.
Oh, really?
Yeah, Google Benchmark, which is what the project was originally using, isn't just a stopwatch. It's a tool that builds the track, fires the starting pistol, manages the water stations, and runs alongside the athletes taking notes.
Oh, wow. So it controls the entire environment.
Completely. And originally, Alago Crop was heavily reliant on that massive infrastructure. The status quo was this setup with 4 specific benchmark files.
Right. The slide deck lists them as BIML, BIML Compare, BILMI, and BILO Pass.
Exactly. And on top of that, the whole project was being managed by 2 completely different build systems simultaneously.
Which were XMake and CMake, right?
Yes. And Google Benchmark is the absolute heavyweight champion of C++ performance testing. It is the industry standard.
Right.
It's robust, it's heavily documented, it's battle tested by literally millions of developers.
Which raises the obvious question. If it ain't broke, don't fix it. Like, if Google Benchmark was working and giving them the precision they needed to test these 2 math variants, why would Lux036 go through the massive effort of ripping it all out?
Just to replace it with a smaller framework called NanoBench.
Yeah, exactly. Why do that?
Well, it comes down to how the code is structured underneath, and specifically a feature in C++ called macros.
Macros, okay.
Yeah. Google Benchmark relies heavily on macros. Things like the benchmark macro and this block of benchmark main boilerplate code.
Okay, let's explain what a macro actually does, just mechanically speaking, for those who might not write C++ every day.
Sure. A macro is essentially a blind find and replace tool, and it runs before the compiler even looks at your program.
Oh, before the compiler even sees it.
Exactly. So
Yeah.
when you write benchmark and then your function name, you aren't writing actual execution logic. You're using a shorthand.
Right.
The preprocessor sees that macro and automatically expands it into dozens or maybe hundreds of lines of complex tracking code, state loops, timer initializations.
So it hides all the messy mechanisms from the human developer.
Yes, so they can just focus on the word benchmark.
But it's heavy, it's clunky.
Very.
And NanoBench, on the other hand, the new framework, it's what's known as a header-only framework.
Exactly.
It doesn't use those preprocessor macros. Instead, it relies on modern C++ features called lambdas.
Right. And a lambda is fundamentally different from a macro.
How so?
It is a self-contained, anonymous function defined right there in the code. There is no invisible find and replace step happening behind the scenes.
So what you see is what you get.
The execution logic is entirely explicit. There are no invisible state loops managed by the framework, and it allows the developer to use a standard custom main function.
Giving them total, transparent control over the program's flow.
Yes.
So here is the real twist, though. The why behind this entire migration. The switch wasn't just some developer wanting to use the shiny new toy instead of the old reliable one.
No, not at all.
NanoBench has a simpler API, and a simpler API means fewer tokens.
Yes. And this is where the AI era part of the title really comes into play. When an AI coding assistant looks at your code, whether it's Copilot or ChatGPT or whatever, it processes text as tokens.
Right, which are basically fragments of words.
Exactly. And AI models have a limited context window, meaning they can only hold a certain number of tokens in their short-term memory at one time.
I like to think of the macro versus lambda difference like reading a recipe.
Okay, let's hear it.
So a lambda is like a recipe where every single ingredient and every single step is written clearly on one single page. The AI reads it top to bottom, understands the logic, and knows exactly what's happening.
That makes sense.
But a macro, on the other hand, is like a recipe that says, go to page 43 to find out how much flour to use, then go to page 12 to see how to stir it, and oh, by the way, the oven turned itself on 5 minutes ago.
That is a brilliant analogy.
Right. The AI has to jump all over the code base, processing thousands of contextual tokens just to figure out what the benchmark is even doing.
And the more pages it has to turn, the faster it exhausts its context window.
Leading it to get confused and, frankly, hallucinate the wrong code.
That's a really strong way to visualize it. Macros hide complexity from humans, but they actually obscure the mathematical reality from the AI.
The AI just has to guess what the macro is going to expand into.
Exactly.
I have to pause here, though, and push back on this concept just a little bit.
Go for it.
As a developer, my first instinct is, wait, are we literally dumbing down our tools?
I hear that a lot.
I mean, we are ripping out perfectly good industry standard benchmark code and rewriting our entire testing suite just so some AI agent doesn't get confused.
It sounds backward, right?
Yeah, isn't that the tail wagging the dog? Like, should we really be compromising our established engineering standards just to cater to an algorithm's token limit?
It's a completely valid concern, but the source material argues the exact opposite. It's not dumbing down the code.
What is it then?
It's forcing elegance. There is a specific quote from the presentation's lessons learned that encapsulates this perfectly. It says, "The simplest code is the code the AI doesn't have to touch."
The simplest code is the code the AI doesn't have to touch.
Right. Think about why macros exist in the first place. They're a crutch.
Because humans don't want to type all that boilerplate.
Exactly. They allow human developers to type fewer lines of code. But an AI doesn't get fatigued typing out lines of code. It doesn't need human-centric shorthand.
Oh, that is a really good point.
By moving to NanoBench and using pure C++ lambdas, the developer wasn't making the code dumber. They were stripping away unnecessary human abstractions.
Revealing the pure mathematical logic underneath.
Yes. Pure logic is mathematically clear, it's explicit, and it's significantly easier for an AI to parse safely without making fatal translation errors.
You're removing the translation layer entirely.
Exactly.
So, theoretically, this beautiful, elegant streamlining should be absolutely perfect. But as I mentioned right at the start of our deep dives, this migration initially backfired spectacularly.
It really did.
The stopwatch swap broke the race.
Yes, the migration fell into what we can call the automagic trap.
The automagic trap. The granular numbers from the slide deck here are just wild. So the developer makes the switch, they migrate one of the heavy files, BML compare.
Right.
And under the old heavyweight Google benchmark, this test suite took 8 minutes and 10 seconds to run. They swap in the lightweight, elegant NanoBench, run the exact same test on the exact same convex optimization math, and the runtime explodes to 1 hour and 16 minutes.
It's unbelievable. And if your continuous integration pipeline suddenly goes from 8 minutes to over an hour for a single test,
Your development comes to a complete standstill.
it's totally dead in the water.
So what on earth caused that? Did NanoBench just break the underlying code?
No, the math was totally fine. What happened is that NanoBench was actually trying to be too helpful with a feature called automatic iteration estimation.
Okay, automatic iteration estimation. How does that work?
Well, benchmarking frameworks don't just run your code once. To get a statistically significant average, they run the code repeatedly.
Makes sense.
Right. And if the code is incredibly fast, say, just adding 2 integers, it might run it 1,000,000 times in a second.
But if the code is slow, it might only run it like 50 times.
Exactly. Because you don't need 1,000,000 runs to find an average if each run takes 5 seconds.
You'd be sitting there all day.
Exactly. So NanoBench tries to figure out that balance automatically. It runs a quick heuristic, guesses how fast the code is, and assigns an iteration count.
Okay, I think I see where this is going.
Remember the arena we discussed earlier? The AllowGo project is executing O of n squared matrix math.
Right. It is inherently computationally heavy.
Yes. And if the data size scales up even slightly during the test, the processing time quadruples.
Ugh.
Yeah. The automatic estimation feature in NanoBench misjudged the sheer weight of this quadratic scaling.
It looked at the initial milliseconds and basically said, hey, this seems fast enough. Let's run it thousands of times.
Yes, it forced the system into an absurdly high number of iterations.
It's like your smart thermostat checking the weather, seeing that it's a little chilly outside, and deciding it needs to turn your living room into a 120-degree sauna for 3 weeks just to be safe.
That is painfully accurate. It's automated tooling running completely amok because it lacks contextual awareness of the environment it's operating in.
That lack of contextual awareness is the real issue. The tool saw code, but it didn't understand the O of n squared math behind the code.
Exactly.
So how did LIC036 actually fix it? Because an hour-long benchmark is, well, it's completely useless.
The developer had to step in and provide the domain knowledge that the automation lacked.
How so?
The fix detailed in the source was manual tuning. They split the test into 2 separate configurations. Then they dove into the nanobench parameters and hard-coded the epochs and mine epoch iterations.
So they essentially turned off the autopilot.
They overrode the AutoMagic feature entirely. They explicitly told the framework, listen, this is a mathematically heavy test. Do not try to guess. Run it exactly this many times and no more.
And the result of that manual tuning was dramatic. The runtime plummeted from that terrifying 1 hour and 16 minutes down to a blazing fast 1 minute and 27 seconds.
It's amazing.
Which is actually even faster than the original Google benchmark time.
Yeah, it's an incredible performance gain. But, connecting this back to the broader theme of AI in software development, there is a massive lesson hidden in this bug.
What's the lesson?
An AI coding assistant might read the nanobench documentation, see the automatic iteration feature, and confidently apply the default template.
It thinks, great, the tool handles the looping for me. I'll just drop it in.
Right, because the AI doesn't actually understand that the convex optimization math is going to quadruple in execution time.
It sees the syntax, but it doesn't intuitively grasp the mathematical weight.
Exactly. And AI, and frankly, an inexperienced human developer too, needs to recognize when a computational task is simply too expensive for default settings.
You have to know when a framework's automation is going to fail and when to apply manual tuning.
Yes. Automation is an incredibly powerful tool, but it is not a substitute for deep domain knowledge.
So they survived the trap, tuned the epochs, and got the runtime down to under 2 minutes. Let's look at the aftermath. We've ripped out the industry standard. We've wrestled the new lightweight framework into submission.
Right.
What is the final verdict on the code base?
The overarching theme of the aftermath is reduction. The entire code base essentially went on a severe diet.
The file-by-file metrics from the presentation are just incredibly satisfying to look at.
They really are.
By making this switch to nanobench, the developer removed a net total of 256 lines of code across 6 different files.
And they managed to do it in just 2 clean atomic source control commits.
That's so clean. And the core C++ source files, BML, BML compare, BMLI, BM low pass, they all got significantly shorter and easier to read.
And it wasn't just the C++ source code either. The build system files got cleaner too.
Right.
Both the xmake.lua file and the benchcmakelist.txt file shed lines. They completely removed the heavyweight dependency footprint of Google Benchmark and replaced it with a simple single header inclusion.
Which brings up a really fascinating detail from the presentation. We talked earlier about how the project originally had 2 build systems running simultaneously.
Yes, xmake and cmake.
The developer explicitly leaves a warning in the slides about this. They note that keeping both build systems in the project means 2 times the work for an AI agent.
This is honestly one of the most critical insights for the AI era of development. When you have duplicate build systems, you are forcing the AI to maintain 2 parallel sources of truth. If you ask an AI assistant to add a new file to the project, it has to use up its limited token context window to remember to update both the xmake configuration and the cmake configuration.
It's like asking someone to write a book in English and translate it into French simultaneously, sentence by sentence.
Exactly. And if the context window gets exhausted, the translation fails. It dramatically increases the chance of a synchronization error.
Where the AI updates one build system but forgets the other?
Right, which immediately breaks the deployment pipeline. The source explicitly notes that AI should be trained to actively flag dead code, redundant configurations, and unused targets.
Because keeping redundant systems around just in case is actually toxic for an AI assistant's reliability.
Redundancy is the enemy of automated reasoning.
But before they could celebrate the faster CI times, the reduced line count, and the AI-friendly build systems, they had to answer the most important question of all.
Did the math still work?
Exactly. If your benchmark runs in 1 minute instead of 8, but it gives you the wrong answer, you haven't optimized anything.
Correctness is paramount.
So the developer ran an ultimate verification step. Before trusting any of the new performance metrics from Nanobench, they verified that all 125 test cases and all 414 assertions passed.
Every single one.
They proved that the migration was purely a build system and benchmarking change. There were absolutely 0 behavioral changes to the core optimization library.
And crucial to the original premise of the project, they verified that the L variant and the L stable variant produced mathematically identical results.
The stable variant, with its LDLT factorization preventing those microscopic rounding errors, it was truly equivalent to the standard rank 1 variant.
Yep, the math held up.
The stopwatches were swapped, the runners were tested, and the race results were verified. So let's wrap up this journey. The developer of a LIGO cap replaced a heavyweight, macro-laden tool with a lighter, modern alternative.
Right.
The tangible result was 256 fewer lines of code, a continuous integration pipeline that ran in a fraction of the time, and a dramatically simpler API.
But, the intangible result is arguably more important here.
What would you say that is?
They created a safer, more predictable environment for AI-assisted development. By reducing token counts, eliminating hidden framework loops, and removing redundant build systems, they made the code base objectively easier for an AI context window to parse and modify.
Without hallucinating.
Exactly.
Without hallucinating.
It's a complete success story, provided you have the domain knowledge to not fall into the automagic iteration trap along the way.
It proves that as our coding partners change from human engineers to machine learning models, our fundamental definition of what makes good code has to evolve.
Which brings me to a final thought I want to leave you with. Right now, in 2026, we are currently adapting our existing historically human-centric tools to make them easier for AI to read.
We are.
We are actively choosing to write pure lambdas instead of macros because the AI understands them better. We're stripping out abstractions to lower the token count.
But if an AI coding assistant performs significantly better with code that lacks these human-readable shortcuts, are we approaching a future where new software libraries, or even entirely new programming languages, are no longer designed to be readable by humans at all?
That's a profound thought.
Right. Will the syntax of tomorrow be optimized entirely to be digestible for the AI context window, leaving human engineers entirely out of the loop?
Well, if the simplest code is the code the AI doesn't have to touch, maybe the ultimate code base is one the human never has to read.
Something to mull over the next time you read a line of code.